Calculating the correlation coefficient is actually a very similar process in Excel or Numbers or whatever spreadsheet you're using. It's very similar to what we did to find the mean and standard deviation of a frequency distribution. So this data set here, this can be found in the file on the course homepage on the course information module, regression data. It has several different data sets here, but the one we're going to use mostly is this one. It deals with chocolate consumption in kilograms per person annually. So in whichever country this first one is, on average, each person consumes 4.5 kilograms of chocolate per year. The other bit of data that's collected for that country is the number of Nobel laureates, or the number of Nobel Prize winners per 10 million people. So the per 10 million people and the per capita thing kind of, they give you a way to scale it so that you're measuring on an even kind of scale, because obviously a country with, a billion people in it has a greater potential for chocolate consumption and a greater potential for Nobel Prize winners than a country that only has a couple million people. So the per capita and per 10 million kind of scale that. Now, these two bits of data, at a quick glance, you wouldn't think that there's anything to relate them. But that's part of what calculating the correlation coefficient is about. It's about letting the math show us if there's a correlation and how strong that correlation is. Now, remember that nothing about correlation is attempting to show causality. So if we do find these to be correlated, or even to not be correlated, we should not infer the reason that they seem to have that or lack that correlation, but just that they are correlated or not correlated. So the formula has several components to it, but really when you look at it carefully, there's only 6 things that we need. We need the sum of the x values, the sum of the y values. We need the sum of the product of each x times y, the sum of the squared x values, and the sum of the squared y values. And we need to know the sample size, the number of pairs of data there are. So what I'm going to do first is, just to give us some labels to work on, is I'm going to insert an extra row up top here, and I'm going to call the chocolate consumptions my x values, and the Nobel laureates per 10 million people my y values. So in addition to that, we're going to need the xy product. We're going to need the square of the x values and the square of the y values. I'm just going to make this a little bit neater here. Give myself a little bit more space for each of these columns. So we can use cell references to do our calculations, and that way we can copy and paste the formulas very quickly. So to get the product of x times y for this first pair, we would need the x value 4.5 times the y value 5.5. But we're not going to actually type those numbers, we're going to use the cell references. So this cell here, the 4.5, is in column A, row 3. And the y value is in column B, row 3. So I'm going to come to the xy column, and anytime you want to do a calculation, you start out with an equal sign. So I want cell A3 times cell B3. And just hit enter, and it will calculate it by going to those cells and pulling the numbers that are in those cells out and doing the multiplication. Now, we can copy and paste this downward by taking this square in the bottom right corner and clicking on it and dragging, but I don't want to do that just yet because I'm going to have to drag down all 3 columns. And actually, we can drag down all 3 at once if we fill in the top row of all 3. So before I drag down, I'm going to fill in not just the xy, I'm also going to fill in the x squared, which is, well, cell A3 times itself. So equals cell A3. Now, you can either do times and then click cell A3 again, or you can use the exponent caret, which you hit shift and then the number 6, and give it a square. The same thing for y squared, equals y squared. So now that we have all 3 of those done for the first row, what we can do is highlight all 3 and drag all 3 downward. And it will automatically fill them in. Just to kind of spot check that, let's look at this row further down here. I'm going to press the F2 button so that it'll show me the formula and show me the cells that it's referencing. So sure enough, this is the XY column and it is further down. It is in now row 8, and you can see that the cell references have been adjusted to be the X and Y value of the 8th row. The same thing for this, it's A8 squared, and for the Y squared it is B8 squared. So we can do it for a single column at a time, or if we have several columns, we can drag them all and have the cell references update all the way down the line. Now, we need to add up all of the values in the X column and the Y column and the other 3 as well. So we're going to come down here underneath the columns, and I like to give a couple of blank rows there, and we're going to type equals sum, open parentheses, and then we can click and drag the whole list of the X values. Close the parentheses, and there it is. That's the sum of our X's. Now, the same way we can drag a formula down, we can also drag it sideways. And again, it will update the cell references appropriately, so that this is now the sum of the Y column. And this one is the sum of the X squared column. So now they've all been updated, the formulas. So in this, we now need to know the number of ordered pairs. And if they started at the very, very top, we could just use the cell number, but unfortunately we can't here because the last part is in cell 25, but we do have a couple of rows for column headers. So there's a couple ways we can do this. Probably the simplest is to pay attention to this block up here in the upper left, the one that actually tells us the current cell that's highlighted. As I drag and highlight, you're going to see this change to tell me the dimensions of what of the section I'm highlighting. So it'll tell me how many rows and how many columns. So as I drag down the X's here, you'll notice that number of rows counting upward. And once I've gotten all of them, that'll tell you how many rows, how many data pairs there are. So there are 23 data pairs. So I'm just going to put that there so we have it. So what we've got now is from these 6 values, we've got everything we need to evaluate the formula. All we have to do is plug them in the proper place and do the calculation. Now, the actual calculation of this, the actual correlation coefficient, is not as horrible as you might think. Again, just toss it in the calculator. We have the n, which is 23, times the sum of the xy column, that is 2072.23, minus the sum of the x's, 133.5, times the sum of the y's, 255.4. In the denominator, we have two radicals, and they're actually very similar. One is entirely with the x's, the other is entirely with the y's. So we have, under the first radical, we have n, which is 23, times the sum of the squared x's. That's 1011.45. Minus the square of the sum of the x's. So we need to be very careful now. There's a distinction between the sum of the squared x's and the sum of the x's, which then gets squared. So in this case, in this part of the formula, we want 133.5 squared. In the next radical, it's actually the same thing but with the y's. So again, n is 23 times the sum of the y squared, 5,130.14, minus the sum of the y's, which is then squared. Now that's an awful lot to type all in the calculator at once, so it's probably better to do a little bit at a time, like to type in the numerator and get that value. And the values are going to be probably large and ugly. It's just the nature of the beast here. You can then do a second calculation for the value underneath the first radical in the denominator, and a third calculation for the value underneath the second radical in the denominator. And then once you have those three values in, it becomes a little bit simpler to type in. But in any case, what you should get at the end of this is that r is equal to 0.8006. It's got more decimal places beyond that. The calculator will show you up to the 10th decimal place, but we get 0.8006. 4 decimal places is usually fine. That's actually not a bad correlation. That's actually fairly strong. There are rules, as you would see in Stats 2, for how you determine whether it's strong enough for what we're doing, but the fact of the matter is that regardless, 0.8 is actually pretty strong. It's definitely way closer to 1 than it is to 0. So it's a decently strong correlation, which might seem surprising. I mean, you wouldn't, as we said before, you wouldn't naturally think that the amount of chocolate a country eats and the number of Nobel Prize winners there are should have anything to do with each other, but here we are. They do. Or at least they seem to. Now, again, this does not explore the reason why they seem to have a correlation, just that they seem to. One other thing we can do while we're here is create a scatter plot, because now that we have this, we might want to actually look at the scatter plot and see for ourselves, does it have something of a decently strong correlation? So, to create a chart, and it's been a while since we've done this, so I'm just going to run through it again. You go to the Insert tab on the ribbon up here, and all the different charts are listed here. We're going to be looking for this little icon with that looks like just yellow or orange and blue dots, and there are several options here. Of course, most of them are nothing you would probably ever need to use, to be honest. We just want the very basic scatter plot here. Now, before I click on it, we probably want to select our data. So I'm going to come over here and highlight the data, including the titles of the columns. And then I'll come back up here and insert the scatter plot. And what we can see is actually not a horrible correlation here. It's actually not all that bad, kind of along the line roughly like this. There are some points that deviate kind of greatly from that line, but for the most part, they seem to be relatively well fitting a positive correlation. So, that's it's not perfect, definitely, and our correlation coefficient is not perfect either. It's 0.8, but that seems reasonable for demonstrating a positive linear trend. Again, none of this attempts to explain why these things appear to be correlated, simply that they do have a correlation. But again, not very much different than any of the things we've done previously in Excel. And again, in the Numbers app, it's very, very much the same. Can this be done on the calculator? Yes, but I wouldn't recommend it because you have to type in every data set, and some of them can get quite large. Remember that there's 2 data values for each member of the sample, so 23 members of the sample means you'd have to type 46 numbers in to your calculator to make this work. And it does get kind of ugly in getting the other columns and whatnot and getting the sums. So it's really inefficient way to do it. But it can even do the scatter plot if you really want to, or if you're in a pinch, it's one way to do it. But I would suggest a spreadsheet program like Excel or Numbers would be the way to go. And again, it works very, very much the same way in either program. And this should all have been, I hope, very reminiscent of what we saw back in Chapter 2, way back in like the early part of February.